Alright, moving right along. Let's take a look at question number 21. Alright, assume that the significance level alpha is 0.05. Use the given information to find the p-value and the critical value. Alright, so we've already, or they give you the test statistic, so you don't have to find that. Remember, the test statistic formula will vary with these tests depending on, what type of claim that we have. This claim says the claim is p is less than 0.2. That's a proportion, so again, we didn't have to figure this test statistic out, but if we did, we would have to use the formula that follows proportions. Anyway, this says that the claim is p is less than 0.2. That less than is very important with this test, because the next question is what is the p-value? So with the p-value test, less than, greater than, or equal to in your claim will make a difference. If your claim has less than, then it is a left-tailed test. If it has greater than, it's a right-tailed test. And if your claim has equal to, it is a two-tailed test. So why does this make a difference? When calculating the p-value, and this isn't proportion p, so don't get this confused. P-value is one way of testing a claim. And so there's a very helpful chart in your textbook or your ebook. It is figure 8.4 and 8.2, and it tells you how to calculate a p-value. So any problem that says what is the p-value, using the means that we have, we need to first figure out or look at the claim and see, is this left-tailed, is this right-tailed, or is this two-tailed? Okay? And so once we figure that out, then we just follow the line. If it's two-tailed here, we have to say, is the test statistic to the right or left of the center of the set of data? Okay? And so left or right, we do what it says. P-value equals twice the area to the left of the statistic if it's left, twice the area to the right of the test statistic if it's right. If it's left-tailed, you just take the area to the left of the test statistic. If it's right-tailed, you take the area to the right of the test statistic. Okay, that's how you find p-values. So let's go back to our problem. Our problem says, what is the p-value? So what we need to look at to figure out our p-value, less than, so this is left-tailed. So to calculate the p-value, I'm going to use this test statistic, and since it says that it is, or that means it's left-tailed, I'm going to take the area to the left of the test statistic. Okay, so I'm going to go to my table, and my test statistic was negative 1.59, so go to the negative z-score chart, negative 1.5, and then 9, this is the nines column. Remember, area in the z-score chart is cumulative left to right, so this is the area to the left of the test statistic, 0.0559. Okay, so our p-value on number 21 is 0.0559. 0.559. So using the p-value is one way to test a claim. The other way that we test a claim is by the traditional approach, and with that we need the critical values. So if we were using the p-value test, of course we have to find the p-value. If we're doing a more traditional approach, then we have to find the critical value. Okay, so how do we find that critical value? Alright, so to find that value, remember, how do we find critical z values? That's what we're looking for, critical z. The only difference with this is that if we need a critical z value, do you remember what that depended on? That depended on your confidence level with intervals. Well, here is your alpha. Alpha is 0.05. We weren't given a percentage. With hypothesis testing, either alpha's gonna, most of the time, alpha's gonna be 0.05 or 0.01. Okay, so we have to go to our table, and we want to get as close as possible to 0.05. Now you may be thinking, wait just a second. Usually when we find critical values, we say alpha divided by 2. And if alpha is 0.05, then why aren't we looking up an area of 0.025? Well, remember, we figured out at the beginning this thing was left-tailed. All the ones that we've done so far, or that we've done in the previous sections, we had 2 critical values, and they were actually two-tailed. We just didn't call it that. Alright, well, with this left-tailed test, we just have this left tail, and that's what we're worried about, because that's where our claim is going to be, just around that area. So we actually, instead of wanting that area to be 0.025, we want that area to be 0.05. So let's go back to our chart. Get as close to 0.05 as possible. There's 0.0505, there's 0.0495, and there's a star right there. There's a star there because that is a common value. Look, the common value is negative 1.645. So our critical value is negative 1.645. So why does that say 1.65? That's because if we round to 2 decimal places, that's what it says to do, then it's negative 1.65. And actually, look, it will take negative 1.65 and negative 1.64. Okay. Let's go to the next question. All right, assume a significance level of alpha equals 0.05 and use the given information to complete parts A and B below. Original claim: the proportion of male golfers is less than 0.8. The hypothesis test results in a p-value of 0.064. All right. So we were told our original claim, it's very important that we write that down. Male golfer, the proportion of male golfers is less than 0.8. So P is less than 0.8. Alright, so now we need to write down the p-value. We didn't have to find it, it was given. So if you need a good reference of how do I work or test a hypothesis with the p-value method, then the first thing that you would do is you'd write down p is less than 0.8. And then you'd find your alternate null hypothesis, and then you would find your p-value through some information that was given in the problem. But this one already gives us a p-value, so the p-value is 0.064. So p-value, this is different again than this p. This is a proportion. This is a p-value. Now, state a conclusion about the null hypothesis. And either we're going to reject A sub O, H sub O, that's our null hypothesis, or we're going to fail to reject H sub O. So reject H sub O, fail to reject H sub O. That's our two options. And the way that you can tell if you're going to reject or fail to reject is your p-value contained in the place where your critical number is? Or actually, is it contained in the critical region? Okay. So you say, well, how would I know that? Well, this is a left-tailed test. Because that's the original claim. And so if I was looking at this under a curve like this, under your bell curve, we have some value right here, some critical value. We don't know what it is, and it doesn't matter because we've already found the p-value. But let's say we have some critical z right here. And remember that alpha corresponds to an area. We were given in the problem that alpha equals 0.05. So we have an area right here of 0.05. We found a p-value. If this p-value is less than this area here, then we will reject the null hypothesis. If this p-value is greater than this area here, then we will fail to reject the null hypothesis. Okay, so let's go back and rewind and listen to that again if you need to. Let's see. So we want to state a conclusion about the null hypothesis. Here's our original claim. Proportion of male golfers is less than 0.8. So our p-value is smaller than our significance level, or our p-value is greater than our significance level. Those are my two options. 0.06 is larger than 0.05. So I will fail to reject my null hypothesis because this p-value is greater than your significance level. All right? Right here, fail to reject H sub O because the p-value is greater than the significance level. So that's how you can tell if you need to reject or fail to reject the null hypothesis H sub O using the p-value test. If your p-value is larger than the given significance level, you fail to reject. If your p-value is less than the given significance level, then you reject. Okay? Without using technical terms, state a final conclusion that addresses the original claim. So remember the original claim? the proportion of male golfers is less than 0.8. Okay? So we would say there is not sufficient evidence to support the claim that the proportion of golfers is less than 0.8. All right? There is not sufficient evidence to support the claim that the proportion of male golfers is less than 0.8. All right, moving right along. In a Harris poll, adults were asked if they are in favor of abolishing the penny. Among the responses, 1,251 answered no, 471 answered yes, and 399 had no opinion. What is the sample proportion of yes responses, and what notation is used to present it? Okay. So, this is a sample. So the notation for a sample proportion is p hat. So that's the notation we need to use. I see responses for no, responses for yes, and responses for no opinion. I don't see a total number though. So this may be how this problem's trying to trick you a little bit. Remember, to get a proportion, it's part over total. And so if we want to know the proportion of yeses, we have 471 yeses. So $471, but we don't know out of how many. You know, don't make the mistake of just choosing the large number as your total. That's not right. So let me get a calculator real quick. And I'm going to add up all of these responses. 1251 plus 471 plus 399. 2121. Okay, so it is 471 divided by 2121. If I had to guess, they probably want a decimal on that one. Well, actually, it's given to us, so we don't have to calculate it. Let's see which one of these it is. Let's take our calculator and we want to say 471 divided by 2121. Alright, and looks like they round to 3 places. So if you round right here, that will be 0.222. And so we use p hat because it is a sample proportion. And 0.222 is the answer. So the answer is C. Alright. A certain drug is used to treat asthma. In a clinical trial of the drug, 20 of 288 treated subjects experienced headaches. The accompanying calculator display shows the results from a test of the claim that less than 8% of the treated subjects experienced headaches. Use the normal distribution as an approximation to the binomial distribution and assume that, assume a 0.05 significance level to complete parts A through E. Alright, so this right here, it says this little readout here, this tells us the original claim, and it'll be a proportion, so P is less than 0.08, that's the 8%. So that's the original claim. We have a test statistic here. Z equals negative 0.660295645. That's pretty long. I'm not going to write that down. You have a P. This P right here would be the true population proportion. And P hat. P hat is your sample proportion, and then N equals 288, that's the number of people in the study. Okay, so our original claim was P is less than 0.08. The first question is the test two-tailed, left-tailed, or right-tailed? Since it was less than here, it's left-tailed. If it would have been greater than, it would be right-tailed. If it would have been equal to, it would be two-tailed. But this one was less than, so it's left-tailed. What is the test statistic? Well, I was hoping I was going to get to actually work one out. I'm sure that I'll get the option of working out a test statistic soon. But the actual test statistic was given to us right here. Z equals. Okay, and round the 2 decimal places, so that will be negative 0.66. What is the p-value? Okay, I assume that this p right here was the population p, but it appears that this p, in whatever type of display this was, so I don't know what kind of calculator this was, the p-value was found to be 0.2545320621. Okay, and so we could probably get close to that if we wanted to, but let's just take their word for it. And then so you just copy it down here. What is the null hypothesis? Okay, so we can at least practice that a little bit. So the original claim was that the proportion is less than 0.08. So we write that down. Then we write the opposite. That's p is greater than or equal to 0.08. Take the one with equality and make it equals. That is our null hypothesis. Our alternate hypothesis is the other claim, which in this case happens to be the original claim. Okay? So you can see the null hypothesis, same thing we had. H sub O, P equals 0.08. Alright, decide whether to reject the null hypothesis. And that means either we're going to reject H sub O or we're going to fail to reject H sub O. Okay? And so to do that, we need the p-value. For the p-value test, we need to look at the significance level. So go back into the problem and look for the significance level. We have a significance level of 0.05. Alright, so we need to look at the p-value. If the p-value is greater than 0.05, then we're going to fail to reject the null hypothesis. If the p-value is less than 0.05, we will reject the null hypothesis. So this is the p-value right here. P equals 0.254532. Well, that's way bigger than 0.05. So you need to do what? If that's bigger, then you fail to reject. All right, here's a statement down here. Fail to reject the null hypothesis because the p-value is greater than the significance level alpha. Okay. What is the final conclusion? There is not significant evidence to support the claim that less than 8% of the treated subjects experienced headaches. Okay. Alright, so now I just want to review a little bit. The actual wording of your final conclusion, I know, probably seems almost sometimes opposite of what you think that it would be. So how do we know how to word that? Well, just as a little review, the wording of the final conclusion. Okay? So if the original claim does not include equality and you reject H sub O, then you say there is sufficient evidence to support the claim. If the original claim does not include equality and you fail to reject H sub O, that's what we did in our previous problem, then you say there is not sufficient evidence to support the claim. If the original claim includes equality and you reject H sub O, there is sufficient evidence to warrant rejection of the claim that. And if the original claim includes equality and you fail to reject H sub O, there is not sufficient evidence to warrant rejection of that claim. And that's on page 391 if you need to go in and look at that. That little chart right there, that is how you work the last problem on a couple of these test questions. So just in case that was giving you trouble, figured I would pull that back up for you. Alright, so we worked through 24. Now on to 25. Here we're given all of our information again. We haven't had to calculate any of that. Let's see what this is. A survey of 1,606 randomly selected adults showed that 587 of them have heard of a new electronic reader. The accompanying technology display results from a test of the claim that 32% of the adults have heard of the new electronic reader. Use the normal distribution as an approximation to the binomial distribution and assume a 0.01 significance level to complete parts A through E. So this time we have an alpha of 0.01. Alright, so our claim was 32% of adults have heard. So that's what? So we have a claim that 32% have heard. So that would be equals. If it's less than 32%, then we'd have left-tailed. Right would be greater than, and the actual claim, the 32%, that means equal to. Okay. So when we have equal to with our original claim, two-tailed. So part A is two-tailed. Okay. What is the test statistic? It's given to us in this box right here. So round the two places like it says 3.91. What is the p-value? 0.0001. That is a super small number. What is the null hypothesis? Alright, so let's see. Remember the original claim was 32%. Alright. So P equals 0.32. That's the original claim. So remember, we'll write that down and then we write the opposite. Not equal to. The one that has equality, that is our null hypothesis. The other one, that is our alternate hypothesis. Alright, so our null hypothesis was the one with equality equals. Alright, choose the correct answer. So do we reject or fail to reject? We had a significance level of 0.01. So that is 1/100th. Our p-value was 1/10,000th. That is less than our significance level. So that means that we will reject the null hypothesis. Reject the null hypothesis because the p-value is less than or equal to the significance level 0.01. That is said alpha. Alright, so you want to see if we can word this right. So what did we do? We rejected the null hypothesis. Was that the original claim? Yes, it was. Remember, it was P equals. So the original claim included equality and we rejected it. So it'll start out, there is sufficient evidence to warrant rejection of the claim that, okay, there is sufficient evidence to warrant the rejection that the claim that, and then our claim, 32% of adults have heard of the new electronic reader. Alright, in a study of pregnant women and their ability to correctly predict the sex of their baby. 57 of the pregnant women had 12 years of education or less, and 43.9% of them correctly predicted the sex of their baby. Use a 0.01 significance level to test the claim that these women have no ability to predict the sex of their baby, and the results are not significantly different from those that would be expected with random guess. Identify the null hypothesis, the alternate hypothesis, test statistic, p-value, conclusion about the null hypothesis, and final conclusion that addresses the original claim. Use the p-method value. Okay. Use the normal distribution as an approximation of the binomial distribution. All right. So we need to first write down our original claim. All right. And so we are saying test the claim that the women have no ability to predict the sex of their baby. Okay? So our original claim is that they don't have an ability to predict the sex of their baby, and the results are not significantly different from those that would be expected with random guesses. So this is a little tricky. The proportion that we use here is going to be, we're saying that it's not what we expect. So not what we expect would be p is not equal to 0.5, 1 out of 2, or 0.5. The opposite of that is p equals 0.5. Our null hypothesis is p equals 0.5, and our alternate hypothesis is p is not equal to 0.5. Now that wasn't our original claim. Our original claim was it's not equal, and our so we come up with this one, which ended up being our null hypothesis. So p equals 0.5 is the null hypothesis. Let's see. That is B. P equals 0.5 is the null hypothesis. The alternate hypothesis is the other one. Okay. All right, the test statistic Z. In your book, there's a table of how to find the test statistics depending on the parameter. Now, I know we've mainly just been dealing with proportions, but we have different test statistics depending on which parameter we're talking about. And they're fairly, they're about the same as what you would expect when compared to Chapter 7 when we were doing confidence intervals. Do you remember, I believe it was 7.2, we were talking about proportions and we used Z distribution. When we started talking about mean, there was two options. Either we know the standard deviation of the population or we don't. If we don't here, then it's a T distribution. So use this formula for your test statistic. If we do know the population standard deviation, then we use this Z. And then the last section in Chapter 7, that's where we went over the chi-square distribution. And we use that when we're talking about standard deviation or variance. Okay. So for our test statistic, since we're dealing with proportions, we want to use this formula here. So p hat minus p over the square root of pq over n. So our test statistic, square root of pq over n. All right. So remember, p hat is the sample. P is the that's the population proportion. That's the sample proportion. Okay. So, all right, P, the population, is going to be the one that that we used for our original claim. That's going to be the, what the whole world would think, that women would probably be able to guess the sex of their baby 1 out of every 2 times, or 50% chance, or 0.5. That's going to be our population. The actual statistic, or the proportion from the sample, is 43.9. That's where we had the study that they did, the small study. So here P is 0.439. Okay. So P hat, that is from the sample. That's 0.439, 43.9%, minus the one of the world. Everybody would probably say about half the time. Maybe not all mothers. Some mothers may think they can predict, and that's fine. All right, and then this P is this P down here, so it's 0.5 times 0.5 over N. What is N? How many did we have here? We had 57. Okay, so over 57. So we'll break out the calculator. What I'm going to do is I'm going to work out the numerator first and write that down. So that's negative 0.061 over, and now I've got to figure out what that is. That's going to give me some crazy decimals, so I'm going to write it down. 0.5 times 0.5 divided by 57. So crazy long decimal, and then I got to take the square root of that. And so when I write this down, just like anything else, I'm probably going to take it out a few more decimal places than I actually need to, but better safe than sorry. So 0.066226661. All right, that's good. 0.066226661. All right, so remember that's negative, so I'm typing that in, hit the plus or minus, make it negative, divided by 0.6622661. And I think I pushed the wrong button. Let's see. Divided by 0.066226661. Alright, that looks good. Looks a little better. Okay, so if this is our answer, and this is a z-score, then how many places should we round this to? And let's see. If I round this to 2 places, since it's a z-score, that's negative 0.92. It's about negative 0.92. Oh, I'm off a little bit. Well, actually, if you look here, it does say that it would take the answer. So maybe I should not have rounded, or I shouldn't have stopped where I did. I should have just kept going and had more decimal places, because you see it did cause a little error there. But my answer is technically right, because it would still take it. Alright, now we need to find, that's the test statistic, we need to find the p-value. So with the p-value, what do we have to do? We're going to have to use the significance level. Okay. So we probably need to go to our chart. We will need this z-score chart eventually, but When we find the p-value method, remember it's very important to remember your original claim. Is it equal, is it less, or is it greater than? So I'm going to have to go back to that chart. Alright, I'll be there in a second. So here's the chart. Was it left-tailed? Were we looking at less than? Were we looking at greater than? Or were we looking at equal to? Okay, and so ours was equal to. Is the test statistic to the right or left of center? So if it's to the left, that means that the test statistic was negative. If it was to the right, the test statistic was positive. So our test statistic in our problem that we figured out by using the little formula was negative 0.92. So we want our p-value is going to equal twice the area to the left of the test statistic. So we have to use the test statistic in our table. Go to your z-score table. Alright, and our z-score was negative 0.92. Now it's good that ours was to the left, because remember this chart shows area cumulative up to that point. So since ours was on the left, pretend this was our test statistic right here, then we can actually just use our test statistic and then just say twice whatever we get. Now if we would have been to the right, remember you could use the test statistic, but then you'd have to say 1 minus to get the area of the stuff over here, and then say that times 2. So again, but our test statistic was to the left. So let's look it up. It was negative 0.92. Negative 0.9012. Alright, so this is the area to the left of our test statistic, 0.1788. Okay, so we had a test statistic of negative 0.92, and under the curve there at a test statistic of negative 0.92, we had 0.1788. Alright, and according to that chart, we have to say 2 times that. So our p-value is equal to 2 times 0.1788. And again, it's 2 times because it was two-tailed, and then we were to the left of the center, to the left. So whatever area we look up, when we look up a z-score of negative 0.92, is going to be the actual area. So you say that just times 2, and this is our p-value. Okay, so let's see what our p-value is. 0.1788 times 2. 0.3576. All right. Once again, you say, well, that's not what's there. What's there is 0.3538. We'll hover over it. You see my answer is there, 0.3576. And you say, why does it list so many different answers? Well, that's because if you use 0.39 plus or minus 100th, so that could be 0.394, 0.392, 0.391. If you use any of those, this answer was correct. So that means that this has to also take a lot of different answers. Okay? And our answer, 0.3576, is down there. Okay. So our p-value, that is that going to be larger or is that going to be smaller than the significance level? Wow, it's way larger. Our significance level was 0.01. Our p-value is 0.35. So it is so many times much larger than that. So that means we fail to reject H sub O. So fail to reject H sub O. There is not sufficient evidence to warrant rejection of the claim that these women have no ability to predict the sex of their baby. The results for these women with 12 years of education or less suggest that their percentage of correct predictions is not very different from results expected with random guesses. Okay. All right, in statistics, what does DF denote? Well, we all know that. That's degrees of freedom. If a simple random sample of 25 speeds of cars on California Highway 405 is to be used to test a claim that the sample values from a population with a mean greater than the posted speed limit is 65 miles per hour, what is the specific value of DF? You take the N, we have 25 speeds of cars, and you subtract 1. So 24. DF denotes the degrees of freedom. For this sample, DF equals 24. All right, using a table of critical t-values of the t-distribution, find the range of values for the p-value for testing a claim about a mean body temperature of healthy adults for a left-tailed test with n equals 12 and test statistic t equals 0.3424. So this is number 28. N equals 12. T equals negative 3.424. And we want to find a range of values for the p-value. This one can be a little tricky. Let's pull up this chart here. Our test statistic is negative 3.424. So, test statistics, remember, for Z or T distribution are symmetric. So we could use a positive 3.424 if we wanted to, and that's probably what we're going to have to use, because if you look at this chart, you don't see any negative values in here. They're all positive. So we're going to use the positive test statistic t equals positive 3.424. All right, so n equals 12, so our degrees of freedom would be 12 minus 1, or 11. So let's go down to 11, and let's see where is our test statistic, which we're going to use positive 424, in relation to these different values here in 11. So if our test statistic was, say, here, which it's not, because ours is 3.4 something, then we would look at the area in one tail, since we had a left-tailed test. That is only one. Left or right, it's only one. And our p-value would be between these two numbers. Well, what was our value? It's at 3.424. All right. And if we look at these values, ours is actually larger than every one of these. So ours would be over here, right? So go up here to right there, 0.005. So the p-value, the range of values, will be less than 0.005. Like I said, it's a little, tricky the way that this problem is and the way that you have to find the answers, but more than likely the one of your tests is going to be very similar to that one. Okay, so we're going to do the same thing right here. We're going to use the table of critical t-values and the t-distribution. Find the range of values for the p-value for a two-tailed test. Okay, so we're going to use a different column, two-tailed. We have to look at those values actually. With n equals 16 and test statistic 1.606. Okay, so let's pull that up. Remember, n was 16, so that means that we need to go to degrees of freedom 15. Now, where would our test statistic lie? Well, it was positive, so we don't have to make it positive. So ours 1.606. 1.606 is between 1.753 and 1.341. So we're right here between these two columns. Now, we were told that it was two-tailed. So when we go up here, look at the area in two-tailed. So we got 0.10, 0.20. So we're right here in between. All right, it's going to be greater than 0.10, less than 0.20. All right. For the following claim, find the null and alternate hypothesis, test statistic, p-value, critical value, and draw a conclusion. Assume that a simple random sample has been selected from a normally distributed population. Answers part A through E. All right, here's the claim. The mean IQ score of statistics professors is greater than 119. Okay? So greater than 119. And that was mean. So mean greater than 119. All right. So what we need to do, we need to identify the null and alternate hypothesis first. That's what it asked us for. So that was our original claim. So that means our other claim that we'll make will be less than or equal to. The one with equality, we take it and we make it equals. And that's going to be our null hypothesis. Our alternate hypothesis then will be the other one, and just so happens to be our original claim. All right, so that is our null and alternate hypothesis. All right, so mu equals 119. And then mu is greater than 119 for our alternate. All right, so it's B. Determine the test statistic. So we have the sample data up there. We are dealing with mean. So the big question is, do we know the population standard deviation? It wasn't given in the problem, so let's just assume that we don't know it. So why does that make a difference? Well, if the population standard deviation is unknown, that means it's the t-distribution. What's another way you can see that? Determine the test statistic t. So, yeah, okay, it tells us it's the t-distribution. I didn't actually have to go that far as I did, but that's okay. So we need to remember the formula for the test statistic t. All right, and that's going to be in our book. I don't remember those formulas. I definitely don't expect you to remember those. I remember in 8T though, 8.2 somewhere, there was a chart. I want to say it was 8-3, but I can't remember. No, 8-2. And in this we have the different formulas. So here's the t statistic for mean. We're going to use this formula. T equals x bar minus mu over s divided by the square root of n. Okay, so that's what we're going to use. Let me double check the formula. It's always good to double check. So x minus mu over, yep, looks right. So we need the information from the problem now, and we can plug those into our formula. Okay, there's our formula there. I know when I click on this it's gonna minimize this, but that's okay. We have n is 21, x bar is 121. That's the sample mean. S, sample standard deviation, is 15. I guess I should have looked at that and saw, hey, this is a t-distribution since we had a sample. But you never know. And then our mu here, our great claim, that's going to be 119. So 121 minus 119 over, S was 15, so it's over 15 over the square root of our n, and our n was, let's see, 21. Alright, so I'll do that in my calculator here. 121 minus 119 is 2. Alright, and then I need to divide it by this right here. So I know I can put it in my calculator if I'm careful enough. Let's see if I can do it. 2 divided by, now I'm going to put parentheses, 15 divided by, and then 21 square root in parentheses. So you see up here, 2 divided by, that's 15 over the square root of 21, equals. Alright, so here's our test statistic. I want to round that to 2 places, right? So that's 0.61. Okay. And so, well, they rounded to 3 places, so 0.611. That's what we had anyway. The next thing is find the p-value. And since it's a t-distribution, we can only really get a range of values. That's what we were doing on the previous problem. So we want to bring up the critical t-values. Okay. And then remember, our degrees of freedom is going to be, we had 21 items, so it's going to be 20. So we're here. And then we need to see where our test statistic lies. Our test statistic was 0.611. So it's going to be less than, okay, was this one-tailed or two-tailed? So think about the original claim. The original claim was that it was greater than. So that means it's right-tailed, so it's one-tailed. So we were 20. Our test statistic was 0.611. That's less than this number. And it was one-tailed because our claim was greater than. So one-tailed, so what does that mean? That means that it's going to be greater than 0.1. So our p-value is greater than 0.1. All right, find the critical value using a t-distribution table. So we just had the t-distribution table, and we'll click on it again. Our degrees of freedom is 20 here. Our significant level is 0.05. So 0.05 in how many tails? One tail, because it was right-tailed. And then 20. So there's my answer right there. One-tailed, 20 is 1.725. So my critical value, 1.725. What is the conclusion? All right, you know, I would suggest using p-value if at all possible. You see this right here? Is this included in our region or is it not? If our p-value is greater than 0.1, is that going to be greater than 0.05? Yes, that's 5/100ths, and that's 1/10. That's larger. So if it's larger, that means it's not in the critical region, so you would fail to reject. Whenever the critical value, or I'm sorry, the p-value is larger than the significance level, then you fail to reject. So it's only two choices here that we could see. We fail to reject that the null hypothesis, reject the null hypothesis, and do not support the claim that mu is greater than 119. Okay, and how do I know? Look at the two: support the claim, do not support the claim. Or remember that chart that told you about the wording? It really depends on if, or depends on, here it is right here, table 8.3. Was it the original claim that we failed to reject? Our original claim was greater than 119. So we failed to reject the null hypothesis. So it was not our original claim. So original claim includes equality or not? It didn't. The original claim was greater than. So original claim does not include equality. And then did we reject or fail to reject? We were failed to reject. There is not sufficient evidence to support the claim that, and then we have our final answer. All right. Number 31. Assume that a researcher wants to use sample data to test a claim that the sample data is from a population with a standard deviation less than 1.8 minutes. The researcher will use a 0.05 significance level to test that claim. If a researcher wants to use a confidence interval method of testing hypothesis, what level of confidence should be used for the confidence interval? Will the conclusion based on the confidence interval be the same as the conclusion based on the hypothesis test that uses p-value method or critical value method? All right, so we want to test a claim that the sample is from a population with a standard deviation less than 1.8. Standard deviation less than 1.8. So less than means that it's going to be left-tailed. All right. So this says, if the researcher wants to use confidence interval method for testing hypothesis, what level of confidence should be used for the confidence interval? Since this is a one-tailed test, it was less than, then we should use a confidence level of 90%. All right. And this is going to come from the reading in the section a little bit more than anything else. We're dealing with standard deviations, so you're going to have a larger range of error there because there's a lot more calculation that goes on with standard deviation or variance. So we don't want to use a smaller confidence level. It's good to be a little broader there. Will the conclusion based on the confidence interval be the same as the conclusion based on a hypothesis test that uses the p-value method or the critical value method? I know that most of the problems we've worked, we use the p-value method, and really it's just because that if you can find the p-value easily, that's probably the easiest way to do it. But you can use either method. So the correct answer is yes. The confidence interval method and the p-value or critical methods always lead to the same conclusion when the tested parameter is the standard deviation. Okay. Which of the following is not a requirement for testing a claim about a standard deviation or variance? So, not a requirement. The sample is a simple random sample. Well, that's just about every test that we do. That's what we want. Population has a normal distribution. That's great. Normal distributions are good. The chi-square distribution is used. So for standard deviation and variance, yes, chi-square is used. The population must be skewed to the right? No, it doesn't have to be skewed to the right. It doesn't have to be skewed to the left. There's no must there. So that's the one that's not a requirement. And the last question, which of the following is not true when testing a claim about the standard deviation or variance? Let's go from the bottom up. The condition of normally distributed population is much stricter requirement for the chi-square test than the t-test or z-test. Yes. The chi-square test is not robust against a departure from normality. Yes. The table for finding p-values does not give exact p-values, as it only includes select values of alpha and selected numbers of degrees of freedom. Yes. The p-value method and the classical method are not equivalent. Whoa, I could stop right there. The p-value method and the classical method are equivalent, so that is not true. All right, that's the last question on the test. Those last couple weren't too bad. They were just kind of conceptual questions. The semester is coming to an end. Hopefully, this week or next week you'll have everything done. Make sure you check your syllabus for the last day of class. Remember, online classes don't always end at the same time as on-ground classes. They usually end earlier. So check your syllabus for the last day of class when everything has to be done. You need to have all of the homework, that's the regular homework assignments and the media assignments done. And you need to have all of your tests and the final exam done. The only proctored test is the midterm. So all the rest are open book, open note. Good luck. Email me if you have any questions.